So this will be the second lecture in the background math chapter of ECE 343. Just a reminder that because this is all background material, I've pre-written the notes and we'll go through it pretty quick. Last time we did take a look at a special case of the complex exponential that was parameterized with a time variable in it. And so we can look at that here. E to the j omega naught t plus theta through Euler's form. We know that can be broken into a cosine piece and a sine piece. One of the ways we can think about this particular signal is that it can be visualized as a vector in the complex plane. It's a unit length vector, so I'm going to go ahead and highlight that in red here. The initial angle, initial being at time t equaling 0, is theta from the positive real axis. And then that guy just sits there and rotates in a counterclockwise way as t increases. That's assuming that omega naught is positive. So this complex exponential is really related to harmonic motion, the motion of rotation. And we have already looked at and proven through using a Taylor series this basic theorem or this basic formula of Euler's that relates the exponential to trigonometric functions. We do know that that parameter omega naught, as it gets bigger, means that that vector will rotate faster. And so it is an angular velocity, if you will, and it helps us decide how quickly this thing is rotating or how fast the oscillations will be. If you look at that in terms of the cosines, this should be familiar. Everybody knows a particular radian frequency as described by omega and should have some comfort with that. So let's make a few notes on this idea of sinusoids and frequency. So I'm going to go ahead and just look at the real part of that exponential, or look at a cosine. Sinusoids are important in the study of electrical engineering. You've seen them before in places like circuits. So we're going to go ahead and just take a look at a signal x of t being equal to cosine omega naught t plus theta. Make sure that we can fully understand this guy. We're going to take in this class t as being measured in seconds. It doesn't have to be that way. It's just a common way, and it's the way we'll adopt in this class. Other situations might require something different, and you would just modify based on that unit of the time variable. We could also write this in terms of a Hertzian frequency by converting between the radian to a Hertzian f naught. F naught is our Hertzian frequency, and that requires a 2 pi factor. So omega naught, just as a reminder then, is a radian frequency. Its units are radians per second. F naught would be the probably more familiar Hertzian frequency, which can be gotten from the radian frequency by multiplying by 2 pi f. So omega equals 2 pi f naught. Both of these are related to how quickly that sinusoid oscillates. As either omega naught or f naught increase, right, the rate of oscillation increase, it becomes higher frequency. So both omega naught and f naught are direct measures of frequency. If we take the reciprocal view of frequency, that gives us the period. So if you looked at frequency before, something like a Hertzian frequency, for example, that's how many cycles occur in 1 second. If I reciprocate that, right, that tells you how many seconds there are in a cycle. So it's the fundamental period. We'll designate that in this class as T naught. So T naught is just 1 over the Hertzian frequency, and it does give us the amount of time it takes for this thing to make one full oscillation. If we wanted to put that in terms of radians, we could just use that same conversion we had before, and we would get 2 pi over omega naught. Since f naught is in cycles per second, t naught is in seconds per cycle. In this class, and oftentimes in engineering, we will define the signal or a signal of frequency omega naught as e to the j omega naught t. This is the most basic component of frequency. This is how we define frequency in this class. So when I talk about frequency content, if I talk about a signal having omega naught frequency content, it's not only talking about the rate of oscillation, which is dictated by omega naught, but it also has something to do with the shape, right? And the shape is dictated by that exponential function. So here for us in this class, frequency means more than just how many times per second something repeats. It's how many times something repeats per second, right? But also that it does so in a sinusoidal way. We're going to learn how important this is as we get to the transform domain analysis in this class later on. You've had some intro to that already, probably in your study or view of Laplace transforms. You might not have known that. Same thing with Z transforms, and same thing with Fourier analysis. If omega naught is greater than 0, we had already mentioned this before, that complex exponential e to the j omega naught t is that unit vector in the complex plane, and it would rotate in a counterclockwise fashion. We oftentimes talk about this as being a positive frequency component. Remember that our most basic unit of frequency, this most basic definition of what we mean by omega naught content, is e to the j omega naught t. That is a complex function of time. It has both a real and imaginary part. We can visualize that as that spinning vector in the complex plane. If omega naught is greater than 0, it spins counterclockwise. If omega naught is less than 0, or a negative frequency, right, the vector rotates clockwise. From Euler's, when we looked at the alternate versions of Euler's, we did come up with an expression for cosine, right, cosine omega naught t, in terms of two complex exponentials. And so really this is somewhat interesting. The idea of a real sinusoid cosine omega naught t is that it's built up of two building blocks. It's got two frequency blocks, right, both complex exponential. One is a positive frequency exponential, a frequency omega naught. The other is a negative frequency exponential, a frequency minus omega naught. So those two guys working in concert, right, create that overall cosine. Basically, the imaginary parts, because those two are conjugates, end up canceling, and we're left with just the real part, and that real part we know to be cosine. So if we think about cosine omega naught t, it has both positive and negative frequency components when we define frequency as meaning this complex exponential content. We can, and we will, we definitely will need to do this for things like the Laplace transform and the Z transform. Generalize our idea of frequency to a complex frequency. We'll designate that with a variable S, so we can go ahead and look at that S. And I'm going to go ahead and put it in rectangular form. Hopefully this looks familiar when you looked at things like Laplace transforms. If it doesn't, I wouldn't worry too much, because we will deal with Laplace transforms in full detail. So as a complex frequency S, we can represent it in our choice of formats, and I'm going to choose a rectangular format, so I'm going to call it sigma plus j omega. So if I look at that generalized frequency, e to the st now, where s is a complex quantity, and then I substitute that s for its rectangular form, and then just use my rules of exponentiation to break it into this form here, I see that that generalized frequency component is representable as e to the sigma t times e to the j omega t. We've already looked at e to the j omega t. We know what that is. That's a rotating vector, right, in the complex plane. It just sits there and spins according to that frequency omega. So that's all about rotation and oscillation. This e to the sigma t out front, sigma is a real quantity. There's no j's up there. So this creates an envelope. If it has a value sigma that is positive, we are going to get a positively growing exponential. So this is for sigma greater than 0. And if sigma was less than 0, we would get a decaying exponential. So what we get here now, right, is this rotation because of the e to the j omega t, but we also have an envelope that allows for exponential growth or decay. If I set sigma equaling to 0, I'd go back to our previous case of just a purely imaginary or an exponential that only has a j in there. The envelope would just hold constant. I would recommend reading the book section on sketching signals. It's really good. I think you should be able to do some basic hand sketching of things, although really in the interest of quality and saving yourself some time, we'll also want to make use of tools like MATLAB, which just make the accurate plot of signals so much easier. We're going to switch gears now just a little bit. We're going to look at what is called the root problem. This is important for us just because we do deal with polynomials, and polynomials are intrinsically related to the root problem. So we'll just get a little bit of background in here. It's also something that if you've never seen the roots problem in the context of complex numbers, you might learn some new tools here. So to begin this, I'm going to start with a puzzle. So to start, let's consider a real quick puzzle. We know that e to the j 2 pi, because we've already studied complex exponentials through Euler's, is equal to cosine 2 pi plus j sine 2 pi. Cosine of 2 pi, right, is just 1. You know that from trig. Sine of 2 pi, well, that's just 0. You know that from trig. So I'm going to get 1 plus j 0, or just 1. So e to the j 2 pi is indeed 1, at least if everything we've learned from trig and what we learned from Euler's and complex exponentials is true. From math, we know that 1 raised to any power, right, is just equal to 1. That's a rule of exponentiation. So I'm going to look at a quantity here. I'm going to look at e to the j 2 pi, and I'm going to raise it to something. I'm going to raise it to a very strange exponent, a 1 over j 2 pi exponent. Because e to the j2 pi is 1, I'm going to get 1 raised to something, and we know from that math fact that 1 raised to the anything is just 1, so I should get 1 out of that. Well, we also know something else from mathematics. We know that if I have a number, call it a, and I raise that to an exponent b, and then I take that whole quantity and I raise it to the c, rules of exponentiation say that's the same as taking a raised to the product b times c. So I can multiply those two exponents and then use that as my exponent for a. So let's go back and take a look at what we had before. We had a base e, right, and it was raised to a power j2 pi, and we raised that again to the power 1 over j2 pi. This other math fact suggests that I should be able to take care of this as e raised to the product of j2 pi over j2 pi. Well, j2 pi over j2 pi is just 1, so that should give me e to the 1, which should just be this number e. Well, we just went through a process on this expression, e to the j2 pi raised to the 1 over j2 pi is coming out to being 1, right? And now we just went through a process and we showed that that same quantity seems to come to e. So that suggests somehow that e is equal to 1. And I think we all know that this is just not possible. E is not 1, e is 2.7 something, right? Everybody's seen that before. So something definitely is going on here. We would like to try to explain this mystery or this puzzle. I think we could stare at this a long time. There's lots of puzzles like this in mathematics. They usually have some connection to something deeper. What I can say is that nothing that I've said so far is actually inaccurate as far as the math rules and the way we look at exponentials. For us to understand this puzzle, we have to understand where this original expression, where this guy really originates and what it means. So let's take a look at that after we look at this root problem. So to solve this puzzle, we're gonna go back to the classic root problem. We're gonna have an unknown variable of interest, call that w, raise that to some power. I'm going to express that as n by m, where n and m are integers, and we're going to let that be equal to some constant, okay? That constant being a constant, it could be a real number, it could be a complex number. I'm going to represent it in polar form, so that's just this alternate side, re to the j theta. And I know in polar form, right, that you could do a full rotation in the complex plane and you'd be at the same spot. So if I was going to draw that out, right, if I come out here to some point in the complex plane, I could think of that as having some angle theta, but I could have also gotten that by doing a full 2 pi plus theta, or I could have gotten it by doing a full 2 pi plus 4 an original angle theta plus 4 pi. So any integer multiple of 2 pi brings us back to the same thing, because going another 2 pi in angle just takes us a full 360 degrees. It brings us a full rotation back and we get to the same part. It is really critical when looking at these root type problems that we include that extra 2 pi k term. It's critical to include that, and we'll see why here in a second. So if I want to solve this, if I want to solve it for w, that's my goal. I want to find out the values of this root problem, things that would satisfy on this. I'm going to raise both sides to the reciprocal of that power, m over n, and that gives me just w, right? So I'm going to get w now on the left-hand side, and I'm going to have my right-hand side, which I wrote in that kind of generalized polar form, and then I'm going to get it raised to the reciprocal, m by n, something along those lines. We know that when we raise something to an integer power, that there are that many distinct solutions. So in this particular case, there should be n distinct solutions to this particular expression. Let's go ahead and run this out. And you get those different distinct solutions, by the way, by plugging in different values of little k. That's why it's so important to have that 2 pi k term in there. If you didn't have that, you would only get a single value. You wouldn't get all the values that were necessary in this. So let me go ahead and do just really quickly an example here. I would like to solve w squared equals 1. I'd like to find the square roots of 1. I think we all have seen this. We know that the square roots of 1 are 1 and minus 1. If I take 1 squared, I get 1. If I take minus 1 squared, I get 1. And there are exactly 2 square roots of 1, right? So I have a variable of interest in this case, right? That's w. It's raised to a power in this case. I'm going to go ahead and let it just be a plain easy integer power 2. And I have some constant off on the right. So this is structured in the way that we were just introducing. I would like to solve this guy. And because I have w raised to an integer power, I know that there's going to be that many unique solutions. That's something that we've seen before in mathematics. If I want to solve this in the way we are introducing here, I want to write 1 in its polar form. Well, 1 is just 1 times e to the j 0. But then we said, hey, you need to make sure you have that plus 2 pi k term in there. That didn't change anything at this point, right? But that 2 pi k is going to be necessary for us to find the different values of this overall expression, the two different unique values. And I could just clean that up a little bit. I could write that as an e to the j 2 pi k. Now I'm going to take both sides of this expression to the 1/2 power. That will give me w on the left, and I'm going to have e to the j 2 pi k divide by 2. That's just going to give me e to the j pi k. So these should be my solutions to this, and this really holds for any k. I could go k equals -1, 0, 1, 2, and so forth. What I'll find out, though, is that if I take a look at what comes out of this for the values 0, 2, 4, 6, all even values of k, I'm going to get one value of w. And then if I look at all the other ones, the odd values, right, I'm going to get the other value. Let's just try it out. So let's put k equaling 0. That tells me w equals e to the j 0. Anything raised to the 0 should just be 1. So one of the square roots of 1 is 1. Okay, and we knew that. 1 squared equals 1. If I pick k equals 1, for example, what do I get? I'm going to get w equals e to the j pi. Well, what is e to the j pi? By Euler's, I know that's cosine pi. That's just -1, plus j sine pi. That's just 0. So I'm going to get -1 out of this. And that's exactly what we also knew. I should get 1 and -1. If I put in different values of k, I'll just see these guys repeated. It's worth pointing out in this particular case, and I didn't do a really great job of my axis here, so let's go ahead and try to do that again, that if I plotted these solutions in a plane, right, what we're going to find out is there's one at 1 and there's one at -1. They're going to be, for this kind of problem, all solutions are going to lie on a circle. They're going to be equally spaced, and there's going to be a number of solutions connected to that original, right, that original power. So let's do another one that you might not have seen before. This is going to be w to the 4th equals 1. I'd like to know the 4th roots of 1. This, again, doesn't have to be terribly difficult. You can already guess that 1 is one of them. If I take 1 and multiply it by 1 4 times over, I do get 1. -1 also works on this, so I should get 1 and -1. It turns out there's a couple more. There should be 4 unique solutions, and it's not too hard to show that j, for example, is 1. J times j is -1, times j again is -j, times j again is going to be that 1. So at least in this case, we know 1 and j and -1 are all solutions, and we're also going to get -j. Let's go ahead and see if the math works out on this. I'm going to write 1 in its generalized polar form. We'd already done that above, so I'm going to just recopy that down. That's e to the j 2 pi k. I'm going to take the 4th root of both sides, and that's going to give me w equaling e to the j pi k by 2, right? Something along those lines. If I look at the different values of k, I'm going to find out, we know e to the j anything is stuff that lies on the unit circle. So if I drew this in this particular case, because my original value, that 1, had a distance of 1, okay, the solutions were all going to lie on this unit circle. And if I put k equaling 0, I'm going to get 1. So I'm going to have a value of 1. That's my k equaling 0 solution. If I put k equaling 1, I'm going to get e to the j pi by 2. Well, that's just j, right? So this is my k equaling 1. This is going to be k equaling 2. I'm going to get -1. And there's going to be k equaling 3. And oh, by the way, k equaling 0 is going to also be true for k equaling 4 and 8 and 12 and so forth on there. All of these guys repeat, but there's only 4 unique ones. So I could get out of this that w equals, and there's a solution set of 4. There's 1, there's j, there's -1, and there's -j. Or you could just write it like this for k equaling 0 all the way up to 3, something like that. You would get a total of 4 unique solutions. Again, because we have a variable raised to a power equal to a constant, we will find always that the solutions lie on a circle, equally spaced, the number of solutions related to that integer power that we're raising it to. Okay, so let's go back to what we had before. W raised to the j 2 pi being equal to 1. Okay, this is a problem. It's a root type problem, and I'm going to write 1 in terms of its generalized exponential form. We already did that before, so I'm just going to go ahead and leave that in there. So I'm going to get e to the j 2 pi k. I'm going to take the j 2 pi root of both sides. That leaves me with w, and I'm going to get e to the j 2 pi k, right, raised to the 1 over j 2 pi. Okay, and what we get out of that when we go through that cancellation is we get e to the k. So when we thought of that original problem way back here, when we were looking at this guy, it was a little bit incomplete because it wasn't showing the intrinsic k, right, that came from this being actually a root problem. And so if we go back up here and we take a look at that particular case, um, we end up seeing that that k term provides us multiple solutions to this. Now, it turns out in this particular case, there's an infinite number of solutions because we didn't have a rational function as my original power. So I could put in a value of k here. K equaling 0, for example, gives me a solution of w equaling 1. That was the first method that we did, right? K equaling 1 gave me a different solution, w equaling e. Both are solutions. Both are coming from that underlying root problem. It doesn't say that 1 equals e, but it does say both are the solutions to an underlying root problem. So hopefully that solves that mystery, that little puzzle. We can also consider logarithms in the context of complex numbers. This is something that many students are just a little less comfortable with than exponentials. But I would just say that logarithms are the other side of the exponential coin. Logarithms and exponentials are brother and sister, if you will. We can, for example, take a look at the exponential problem, e to the b equaling a. That's an expression. Most students are pretty okay with that. A equals something raised to another power. Logarithms are just another expression for that. This e to the b equaling a is 100% equivalent in information to this expression, the natural log of a equaling b. I use natural log here because the base of my exponent, right, was e, something along those lines. These are the same problem. So we will use a lot of the same solution that we had seen before when we were dealing with this root problem, in that we definitely need to include the general polar form when we're taking the logarithm of constants to try to figure out what values can be there. So let's take a look at it. I want to do the logarithm of a complex number w. I'm going to go ahead and take that w and express it in general polar form. So r e to the j theta plus 2 pi k. I know that what? The log of a product. So if I have ln of a times b, I know from math before that that's ln of a plus ln of b, right? That's just basic logarithm behaviors. So I have a product here. I have r times something else. So ln of r times this other thing is going to be expressible as ln of the first thing. So that's ln of r, and then ln of the second thing. But the natural log of e raised to something is just whatever the exponent was. So I'm going to get j theta plus 2 pi k in this case. Okay, so the log of a complex number can definitely result in a complex result. Let's take a look at something that you probably had high school teachers tell you couldn't be done. Let's go ahead and take a look at this idea of taking the natural log of -1. Many of you who have basic calculators, if you put log of -1, it just blows up. It says, nope, you can't do that. It'll give you undefined. I definitely had math teachers myself back in high school who says you can't do that. Well, you can't do it with real numbers, but you certainly can do it with complex numbers. The log of -1 is completely well defined. There's no problem with it. We just need to be able to use the complex number set. So I'm going to express -1 in terms of its generalized polar form. That's going to be 1 e to the j pi, right? That puts us 180 degrees from 1. That's the -1. And then I'm going to put in that 2 pi k part in there as well, because we know that polar form can support any of those 360-degree rotations from that original space. So -1 expressed in generalized polar form is e to the j pi plus 2 pi k. I'm going to go ahead now and apply my rules of logarithms. I'm going to get log of 1, and then I'm going to get log of that other mess, which is just an e to the something. That is just going to give me the something. Log of 1 is 0, so I should get j pi plus 2 pi k. Turns out log of -1 has an infinite number of solutions. If you take complex variable theory in the math department, this is a 400 level math class, you would get to play with some of this stuff and you'd get a little deeper dive into what all this stuff means. This idea that we get an infinite number of solutions is a little problematic for some computer tools. So many tools, such as MATLAB and oftentimes good calculators, they'll just give you one of them. And so if I typed in on MATLAB log of -1, it would give me j pi. It would just give me the k equaling 0 solution. That doesn't mean it's the only solution. It's a solution. Okay, so let's go ahead and switch gears again. We're going to jump to another section in Chapter B. This is all about partial fraction expansions. That gets to be a mouthful, so we're going to go ahead and abbreviate that. So partial fraction expansions, we'll just call it PFE. You should have seen this before. You should have seen this back in your circuits class or math classes. And I think there's a very deep discussion of partial fraction expansions in the book. I'm going to try to go through it pretty quick because generally in math semesters, this is something that people are highly familiar with, and we just don't have to spend a lot of time on it. Still, I'd like to be complete, and because it's a recorded lecture that you can fast forward through, we'll see where we can get with it and make sure I hit most of the details. What's the basic idea of a partial fraction expansion? The basic idea is that we turn a high order rational function into a sum of low order pieces. It's breaking down a function into simpler pieces. We've already seen this strategy before, not exactly in this context, but a Taylor series. What did it do? It turned a function that might be kind of complex and it broke it up into simpler pieces. In the case of a Taylor series, the simpler pieces were just polynomial pieces. For a partial fraction expansion, it has a little bit more of a limitation than a Taylor series because it really is something that applies to a rational function, not just a rational function, but a strictly proper rational function. We'll talk about that in a minute. And it does try to break it into simpler pieces, lower order pieces. We're going to make high use of a partial fraction expansion when we talk transform domain analysis using the Laplace transform and Z transforms. So what is a rational function? A rational function is just a ratio of polynomials in the variable of interest. So I can look at some function of a variable x, let's call it f of x. If it is a rational function, it means that it can be expressed as a polynomial in x in the numerator divided by another polynomial in x in the denominator. So rational function, ratio, right? Rational function is a ratio of polynomials in the variable of interest, in this case x. That top polynomial, we could abbreviate that or just notate it b of x for kind of a shorthand notation. Same thing for the bottom, we'll call it ax. All the coefficients for the terms in there for the numerator, they're going to be little b sub something, right? So b sub m, x to the m, so the subscript on the b is going to match the power of the x, right? We're going to do this in a standard form, which is a descending powers of x. That is also something that we should begin to appreciate, that these standard forms generally are there to make it easier to communicate and also to help us avoid making mistakes. And the bottom is a different polynomial, and so it could have a different order, x of n all the way down to some a of 0. We are going to go ahead and let that first coefficient for the denominator be equal to 1. If it wasn't, you would just divide top and bottom by that coefficient. That doesn't change the expression at all. We can always normalize one of those coefficients just by dividing top and bottom by the coefficient. For reasons that we'll see later, it's convenient to have that highest order power of the denominator be 1. For partial fraction expansions then, f of x needs to be strictly proper. That means that m, the order of the numerator, needs to be less than the order of the denominator. If it isn't, you usually do some sort of long division is one way of handling it. So let's quickly show what a long division looks like. Suppose I had some f of x that I was interested in. It's going to be, in this case, a rational function. So I'm going to write this as x squared plus x plus 1 over x plus 1. The m here is 2. The n is 1. Because n is not greater than m, this is not a strictly proper rational function, and we would need to do some division. So how do we do division? We take that denominator in there, that's this guy, x plus 1, right? And we are going to put it into the numerator, so that's the x squared plus x plus 1, and I'm just going to do long division. How many times does x go into x squared? Well, it goes in x times. X times x is going to give me the x squared, and x times 1 gives me x. Take those guys, subtract them, and I'm left with 1. That 1 is my remainder, right? So this was the quotient, this was the remainder. And you might have to do more than just a single term here. You might have to go a ways before you get your final remainder to get a strictly proper end piece. So when I do this and I re-express this, x squared plus x plus 1 divided by x plus 1 is going to be the quotient. We just got that from long division. That's going to be the x, right? And then I'm going to take the remainder, which only makes sense in terms of the original denominator, which was x plus 1. So I'm going to have the remainder, that's 1, over the original denominator, x plus 1. You could easily demonstrate that this guy is equivalent equivalent to the above one by taking this first term x, right, multiplying it top and bottom by x plus 1 over x plus 1. That's a fancy one, doesn't change it. If you do that multiplication and combine the terms, that's finding a like denominator, you would get the original, original expression. So when we do that long division, we should get polynomial pieces from the division, and then we should also end up with a strictly proper rational function. And it's that strictly proper rational function. In this case, it wouldn't matter because there's only one term. We don't have to simplify it. But most of the times, we would have a denominator that has more than one root. And so we might want to do some additional decomposition using a partial fraction expansion. Okay, so let's now just focus on something that is in strictly proper form and think about what a partial fraction expansion does. We need to factor the denominator. You can use a calculator or MATLAB to do that. So I'm going to retake my rational function, right? I'm going to leave the numerator alone. Don't have to worry about that right now. And I'm just going to re-express the denominator, which was before in standard descending order of the polynomial. And I'm going to root it out and write it in factored form. So an nth order polynomial has n roots. We already looked at that. That was part of that roots problem, right? And the roots here, I'm going to call lambda 1, lambda 2, all the way out through lambda n. In factored form, then, I'm going to have x minus lambda 1, and I'm going to multiply that by x minus lambda 2, all the way through x minus lambda n. If these roots are unique, then the partial fraction expansion takes this nth order denominator polynomial, right? And it allows us to break it up into n first order pieces. So I'm going to get some coefficient k1 over that first denominator root, x minus lambda 1. Some other coefficient k2 over x minus lambda 2, all the way out through some x of k, x of lambda minus n, lambda n. Something along those lines. So I'm going to get n pieces, each first order little functions or little fractions. Our job in the partial fraction expansion is to find those value k's. Those are the things that we need in order to do it. Lots of methods to do this, stuff you should have seen before. There's something called the method of clearing fractions. You basically find the same denominator and equate like coefficients. I'll demonstrate this by example. There's also a method of residues. This is my preferred method. I think it's more systematic. It's something you can program in a computer pretty easily. And so I think it's a kind of a workhorse that just doesn't require a lot of tricks or other things. You do have to do some calculations, but it generally is a pretty robust way of carrying this out. Really no need for shortcuts. That method of residues is also called the Heaviside cover-up method. So we got that Heaviside cover-up method, and it basically says we can get those coefficients as long as the roots were unique as being our original function multiplied by x minus lambda I, and then evaluate at lambda I. So you can read in the book a little bit to get some insight on that, and or just do some derivations on a scratch piece of paper. I think you should be comfortable with these guys. As an example, let's take a look at this rational function. F of x equals 2x squared plus 2x minus 4 over x squared plus 2x plus 3/4. This is not strictly proper, so we need to make it strictly proper before we can go down and break up that quadratic denominator into a sum of two first order pieces. So I'm going to do long division here. I'm going to take that denominator, x squared plus 2x plus 3/4, and I'm going to put it into the numerator, 2x squared plus 2x minus 4. How many times does x squared go into 2x squared? Well, 2 times, right? Then take that 2, right? Going to go ahead and take that 2, multiply it by that original guy, and what do I get? I'm going to get 2x squared plus 4x plus 3/2. Subtract these guys, and I'm left with minus 2x minus 11/2. That remainder, right, has a highest order power of x, is just being x to the 1. My original denominator had a highest power of x squared. I know I've gone far enough in my long division to get a result that is going to be strictly proper. I take my quotient, right? That's this piece. There could be more terms than that. It's not in this case. And then I'm going to take the remainder, and because the remainder order, right, is less than my original denominator order, when I express that remainder over the original denominator, I have a strictly proper rational function. This part's already simple, right? I've got the 2 by itself. Now we need to focus on this guy. That's that rational function, now strictly proper. It's a second order quadratic denominator, right? And I'd like to break this up into a sum of two first order pieces. So let's focus on that. Minus 2x minus 11/2 over x squared plus 2x plus 3/4. First step in that partial fraction expansion is to root the denominator. Rooting the denominator in this case could be done with the quadratic formula. It's not a terribly difficult one. The roots here are pretty easy. They're at minus 3/2 and minus 1/2. So my roots expressed in factored form is going to be x plus 3/2 and x plus 1/2. And And we're ready to go now that we've got it in factored form. What does the PFE say? It says that that quadratic piece, that's this guy, right, can be broken up into a sum of pieces depending on the order of the denominator. Order of the denominator here is 2. They're both unique roots, so I should get a first root that is related to that x plus 3 halves and another one that is related to that x plus a half. I'm trying to find these coefficients k1 and k2. Method of clearing fractions. What do? I take this expression that I just did, that's this guy, right? And I want to make it so that these terms here have the same denominator as this. This first one, right, this guy right here, doesn't have an x plus a half in the denominator. To get an x plus a half in the bottom of that first term, I need to also multiply the numerator by it. That's like multiplying that first term by a fancy 1, right? That's this guy right here. So I'm going to multiply that by x plus a half over x plus a half. That creates a new term whose denominator matches this stuff over here. I'm going to do the same thing for the second term, except for now it gets to be multiplied by x plus 3 halves over x plus 3 halves. I go through all that math and I combine terms. What do I end up with? Left-hand side, same as I expected. It has x plus 3 halves times x plus a half. Because I found the common denominator for these other terms, I get that same piece over here, right? And now what do I know? I know that the numerators also have to equal one another. So I look on the left here, and on the left I see that the x term, right, has a -2 coefficient. There is an x here, and there is an x here. So k1 plus k2 had better be equal to -2. That's an equation, right? I also know on the left hand, the thing without the x is -11 halves. Well, I had a k1 half, k1 times a half, and a k2 times 3 halves. K1 times a half, k2 times 3 halves added together had better give us -11 halves. So that's this piece over here. Two equations, linear in two unknowns. We can solve that guy. I'll let you pick your favorite one. A future lecture, we'll talk about the linear algebra to systematically do that, but I know that's something you've seen before. Here we get k1 equaling 5 halves and k2 being equaling -9 halves. Thus, what do we get out of this? That original rational function f of x, which we had expressed as a non-strictly proper quadratic over a quadratic, can be broken up into simpler terms. And the simpler terms here are the 2 that came out of the synthetic or long division. And then we ended up getting 5 halves over x plus 3 halves and -9 halves over x plus a half. And we got those coefficients 5 halves and -9 halves by the method of clearing fractions. We could also get this with a method of residues, so we'll go ahead and do that as well. It would have been the same thing. F of x being not strictly proper needs to be made strictly proper, plus some other, what they're called our direct terms. We get those through that long division. We've already done that work, so I'm not going to repeat it here. So I'm going to get that too, and then that is my new fraction that I want to break up into my two pieces. I want to get that into a k1 over x plus 3 halves plus a k2 over x plus a half. I'm going to call that now strictly proper rational function piece. I'm going to call that f prime of x, and I want to do a PFE on that. If you go back up to the earlier part in the notes, it says I can get these coefficients, right, by multiplying the fraction, the strictly proper fraction, so f prime of x, I'll call it in this case just to avoid confusion. I'm going to multiply it by the root that I'm trying to find the coefficient for. That's going to be x plus 3 halves, and evaluate at the root. The root is at -3 halves. How do I know that, right? Because x plus 3 halves equaling 0, solve that guy, you get x equaling -3 halves. So the root, right, you kind of get that sign change on there. So if I do that, if I look back at what is my f prime of x, that was this guy. I could have written it in factored form. The denominator would have been x plus 3 halves times x plus a half. Because I'm multiplying by x plus 3 halves, those x plus 3 half up here on top is going to cancel with the x plus 3 halves in the denominator, and that's going to only leave this x plus a half piece. And then I had the original numerator in there. And then I just throw in x equals -3 halves, evaluate that. If you go through all that math, you get 5 halves. No surprise there. That's the exact same result that we had using the other method. It shouldn't matter on the method. The partial fraction should only give a single unique result, so we expect the answers to be the same. This one is just easier to systematize or to make a methodical procedure to carry it out. K2 in the same way, we're going to multiply by the term that's related to the factor we're trying to do. So x plus a half is that denominator term. Multiply that by that fraction, evaluate at the root. If we go through all the math on that, we get -3 or -9 halves. Exact same result as we had before, as expected. I don't really care how you do these. I think you should be able to employ most of the main methods, but it's really maybe a matter of personal preference as to what people like the most. So same result. that is going to get us through this first part on partial fraction expansions. We'll continue with a few additional techniques and topics on our next lecture, the third lecture, which should wrap out Chapter B.